Hi, in this video, I'll talk about using confidence interval to test a hypothesis and how to compute the confidence level given alpha. In a hypothesis testing question, you're given a value of alpha, the significance level. Usually it's 0.05, 0.03, 0.02, around that range. Most of the time, you would compute the p-value and then compare the p-value to alpha. If p-value is less than alpha, you reject H0. But sometimes the question asks you to test a hypothesis using confidence interval instead. For confidence interval, you need a confidence level, right? Usually around 95%, 90%, 98%, in that area. Well, given alpha, what is the corresponding confidence level? Here's the rule. If the test is two-tailed, confidence level equals 1 minus alpha. If the test is one-tailed, confidence level is equal to 1 minus 2 times alpha. I'll show where this rule comes from, but first, let's back up and see how we can use a confidence interval to test a hypothesis in the first place. Suppose here's the claim. Then that means here's the null hypothesis H0. And here's the alternative hypothesis HA. In a hypothesis test, we're trying to decide whether to reject the null hypothesis H0. Suppose we run a confidence interval and arrive at this result. What does that mean? Do we reject the null hypothesis H0 or not? Let's draw a diagram on the number line and figure this out. The parameter is population proportion P. The null hypothesis H0 says that P is equal to 0.75. So what H0 is saying is that P is right here. Let's call this 0.75. And H0 says P is right at this spot. What about the alternative hypothesis HA? HA says P is larger than 0.75. So HA says P is somewhere over here on the right of 0.75. Those are the two hypotheses. The evidence, however, gives rise to the confidence interval. And what does the evidence say? The evidence says that P is somewhere between those two limits. It's somewhere between 0.748 and 0.82. Based on that evidence, can we reject H0? No, because the evidence says maybe H0 is true. Because it could be. The evidence said P could be right there at 0.75. Well, for that matter, the evidence also says maybe HA is true. Because, over there to the right of P, that's possible as well. But then again, maybe to the left of 0.75 as well. So this is a situation similar to when the p-value is larger than alpha, where we don't know if there's evidence of HA and we can't reject H0. Definitely, we cannot reject H0. So here's the general idea. If the confidence interval covers the value in H0, then we do not reject H0. If the confidence interval instead is outside of H0 and completely on the HA side of things, then we reject H0 in favor of HA. That's how a confidence interval is used to test a hypothesis. But how big the confidence interval is depends on the confidence level. If we reduce the confidence level, then the confidence interval also gets smaller, and maybe it got so small, it actually skips over the value in H naught and stays completely on the HA side of thing, in which case with a new confidence level, maybe we would reject H naught. It's similar to working with p-value. We compute the p-value, it's this big. And then we look up the alpha in the problem. If alpha is this small, then p-value is larger than alpha, we don't reject H naught. But if alpha, the given alpha in the problem turns out to be this big, then p-value is smaller than alpha, then we reject H naught. What's happening is that the confidence level that you use is tied to the alpha that you're given in the problem. How? Let's draw some pictures. Here's a diagram for confidence interval. Let's say we take the sampling distribution of the parameter. Then what we do is we put the confidence level in the middle of the sampling distribution. So it's right in the middle, symmetric on both sides like that. And this would be the lower limit, and this would be the upper limit of the confidence interval. But if we switch to the z-score of it, then this point right here would be the critical value z star. That leaves two tails on both sides, and we say that the confidence interval is always two-tailed. A hypothesis test, however, is different. The diagram for a hypothesis test depends on what the alternative hypothesis HA looks like. If HA has a greater than sign, then the diagram is like this, where you have the critical value here, and alpha is the area that's on the greater than side of the critical value. It's on the right side of the critical value, and we say that this is a white-tail test. Now let's look at where the alternative hypothesis has a less than sign like this. HA says P is less than 0.75. Then we would have the critical value over here, and the area to the less than side of the critical value is the alpha. We say that the test is a left-tail test. When HA has the less than sign, we say that the test is left-tail. I'm using examples where the parameter is P proportion, but it's also true when the parameter is mu, the mean, or sigma, the standard deviation, or sigma squared, the variance. And the third situation is when the alternative hypothesis has the not equal sign, in which case we don't require things to be either greater than the 0.75 or less than the 0.75. Either way is fine. If it's greater, great. If it's less than, that's okay too, because they both mean not equal. So we're looking at a situation where being greater than the critical value is perfectly fine, or being less than the critical value on the left side is perfectly good as well. And the total area will have to be alpha, so each of them is alpha over 2. When HA has the not equal sign, it's a two-tailed test with a total area, with a total tail area is alpha. And if the total tail area is going to be alpha, it will be alpha over 2 each tail. So here's a summary. When HA contains a greater than sign, it's a right tail test. When HA contains a less than sign, it's a left tail test. And when HA contains the not equal sign, it's a two tail test. You can visually figure out how to remember that, right? Now, let's relate hypothesis testing to confidence interval. Let's take the last situation first. Here's a diagram for a two-tail hypothesis test. Now let's compare it with the diagram for confidence interval. They look alike. And therefore, it means that the confidence interval here and the white area here are the same. What is the white area? It's the area of the whole curve minus the two tails. Therefore, the confidence level is equal to that white area, which is 1 minus the two tails. Each tail is an alpha over 2. So it's 1 minus 2 times alpha over 2, or equal to 1 minus alpha. Confidence level is equal to 1 minus alpha for a two-tail test. For example, if alpha is equal to 0.05 and the test is two-tail, then the corresponding confidence level is 1 minus 0.05, which is 0.95 or 95%. Now let's look at the white tail situation and let's compare it to the diagram of a confidence interval. They do not look the same. The hypothesis test only has one tail of alpha, whereas the confidence interval has two tails on both sides. So in order to make the hypothesis test look like the confidence interval, we have to pretend that there's another tail on the left, also equal to alpha. With this imaginary extra tail, now the confidence level here and the area there are now equal. That means the confidence level is now equal to the graph minus the blue tail on the right and the red tail on the left, for a total of 2 times the tail, so 2 times the alpha. So the confidence level is 1 minus 2 times alpha for a white tail test. For example, if the problem gives you alpha equals 0.05, but the test is a white tail test where the alternative hypothesis HA has a greater than sign, then the confidence level is actually 1 minus 2 times 0.05, and that makes it a 90% confidence level, not 95%. And now you see that the situation with the left tail test is similar. It matches on the left, but it's missing a tail on the right. So again, we have to imagine an extra tail on the right. Well, the area to the left was alpha, so the area to this new imaginary tail is also alpha. And when we match these two areas together, you can see that confidence level is 1 minus 2 times alpha for a left tail test as well. So that's where we get this rule from. If the test is two-tailed, meaning HA has a not equal sign, then the confidence level is equal to 1 minus alpha. But if the test is one-tailed, HA either has a greater than sign or it has a less than sign, then the confidence level is 1 minus 2 times alpha. Here's a big summary. Hope that helps. Any questions? Please comment below. Subscribe for more contents, and thanks for watching. Bye.